All right, welcome to the very last video in this entire 2020 SANS Holiday Hack Challenge. We have finally reached the end and we are working on Objective 11B, the second part to the blockchain challenge. And in this part, this is where we try to reverse engineer the changes that Jack Frost made to the modified block in the blockchain and discover the SHA-256 hash of the original block before it was modified to basically lean very much so in Jack's favor. So I guess we'll just hop right into it. So if we go over to the challenge, it gives us the SHA-256 hash of the altered block. Now, if you remember, by default, this blockchain uses MD5 as the hashing algorithm, which is why Jack was able to essentially modify the contents of a block on the blockchain, and when being verified with MD5, it did not trigger any discrepancies. And that is because MD5 is known to be insecure. It's known to have hash collision methods that are pretty reliable. And so that's what Jack exploited to be able to get a very hefty nice score. So it says here, you can recreate the original version of that block by changing the values of only 4 bytes of the entire block. Once you've recreated the original block, then we're going to submit the SHA-256 hash of that block. All right, so we've already downloaded our blockchain file and then the boilerplate code. So we don't really have to do anything else here until we get that final hash. So we do have quite a bit of hints and such. So we can take a look at those real quick. So we talked about MD5 hash collisions. This links to this Korkami, I think is how you pronounce it. Collisions repository, which we'll get to. So it says if you have control over bytes in a file, it's easy to create MD5 hash collisions. And we already figured out that anybody can predict those nonce values, so that's not even a problem at this point. This one talks about chaining blocks and that the previous hash is included in the data that's to be hashed the next block. Okay, and then this is what hints at the fact that it uses the unicall method or the unique hash collision method to perform that hash collision, and then it links to a GitHub repository for MD5 hash collisions or hash clash. I believe there's one more. Yep, and then there's a document in that block that Jack modified, and he doesn't remember writing that content. Okay. I believe that might be it for now. Okay, so first things first, what we want to do is figure out what block that Jack actually altered. Now, thing is, if we run this using the blockchain verify or the verify chain function, we actually will not. It will basically say it's valid again because Jack leveraged the MD5 hash collisions. So we can't tell that this blockchain has been modified whatsoever. So what we need to do is, instead of using MD5, use a more secure hash algorithm that's less susceptible to hash collisions, and that was hinted that it should be SHA-256. So to do that, we just have to make some tweaks, which I'll show you here. And so what we do is a for loop for all the blocks. And in the actual code above, what it does is it calls md5.new from crypto.hash. So you can even see the code import SHA-256. So all we need to do is swap out md5.new to SHA-256.new, and then we are as our hash object, and then we are going to call update with the signed block data for each block. Then what we're going to do is extract the hex digest from that, and we're going to compare it with the hex digest that we got from the objective description, which is right here. So we simply copy this and paste it into here. And so once we reach that hex digest, we know that we've located the modified block. And then what I'm doing here is printing basically toString for the block, which is going to print out a bunch of details for it. And finally, I am dumping all the documents associated with that block. So we can go ahead and run that. And okay, so let's just show you the output here. So this is all the data from the one of the files. But so we can see this is the block that was modified. 129459 is the index in the chain. We can see that we have a maximum score of all F's, which is a maximum integer value that the score can hold. The sign is set to nice. So likely that was modified. And then we have two files. We have a random binary blob, which we'll see why that was added later, and then a PDF file. And then both of those we've actually saved out. So if we open the PDF file, we'll use Firefox for that. We can see it's just some sort of a report written by Shinny, which again, if you remember from the hint, Shinny doesn't remember actually writing any of this. And this is all just glowing reviews for Jack. Okay, yet Shinny has no recollection of even writing this. So if we exit out of here, what we need to do, basically there's a few things. So let's start with the PDF. So we were in the hints, we were given a link to this this talk deck about hash collisions. Additionally, we were given a link to this collisions repository. And in here, there's a section on PDFs that talks about collisions with PDFs. And here we have PDF collisions with MD5. So this actually talks about a bit of the structure of a PDF and how it basically uses what are called object numbers and references to define a tree that links together all the different sections of that PDF, like pages. And everything depends here on the root element. So you can see here how some of these are constructed. So things are essentially linking to each other. Okay, and then trailer, which then defines that root object. So what we need to do is, we know that that this PDF document is not what Shinny remembers writing and committing to the blockchain. So chances are there is something funky going on with the PDF. And this talks about how you can basically collide a pair of PDFs together simply by having two document trees in the same file. So what we can do is, I actually just ended up opening this in Vim just regularly and looking at it, because it's really the plain text that we're worried about. We don't care about the actual contents for right now. But we see some of this this content here. It looks like we have some sort of a inline comment, go away Santa, and then we have pages, which then points to object 2, which is down here. Okay. And then this points to next to 23, which is somewhere down here. Okay. So after a lot of looking through this and playing with it, I realized that this object 3 never gets called or acknowledged. So through trial and error, I decided that instead of having this original element point to object 2, why don't I try object 3 and see if that changes anything about it. So I go into replace mode in Vim and just simply make that a 3. Now, if I open that in Firefox, we can see that the document has actually completely changed. It's now all different content, still the same, one page, but now we're getting some details about horrible things that Jack has done. So this just goes to show how you can basically have two different PDF contents in a single file where you can completely hide one so that the user opening this in a PDF viewer never sees it. So we basically uncovered the bad stuff that was hidden in this document in the real report that Shinny probably wrote. So if you read through this, you can see it's a pretty bad act, and so it would make sense that this would actually be a naughty act versus a nice act. So now we're realizing that we're basically making two changes at this point to the block, and one of those is to turn the naughty nice indicator from nice to naughty. So that's basically going to be a 1 to a 0, and we'll see how we can do that in the block. And the second change that we've made is to have this pointer point to the third element rather than the second in the PDF. So that's two changes we've made, and that's essentially only 2 bytes. And we know from hints that we have to make a total of 4 bytes of changes to have this end up as the original document with the same MD5 hash. So from another hint we got, actually before we even step forward, let's go ahead and make that modification to the block where we are changing the nice score to naughty score. So let's go and take a look at some of our code here. And so this is going to save the block out to a file. This is how we would do that. It simply has a save a block function that you can call. So we'll go ahead and save a clean version of that. So I can call that. And that is going to save this here. Okay, and then we're going to make a copy of that, and we'll call it save block modded. Oops. And what we're going to do is simply change the nice naughty bit. So let's see here. So the sign, we are going to change from a 1 to a 0. There we go. So if self.sign is greater than 0, then that means it's nice. Okay, so we need to change the sign from 1 to 0. So what we can do is we want to know where in that block that this is actually changed. So what we'll do is c2.blocks at i.sign equals 0. So we'll just modify that, and then we'll save that out as underscore modded. So we're changing the block and then saving it as the block index underscore modded.block. So we'll go ahead and run that. And now we want to do a diff on the 2 blocks. Okay, so I want to have to remember here how to do a binary diff. Okay, yeah, so let's just do that. So XXD is going to allow us to get like a hex dump of these 2 blocks. So what we'll do is into orig.hex, and then, or just 1.hex is fine, and then xxd underscore modded 2.hex, and then we'll run diff to do a diff on the two files to see where they differ, and we can see here that this hex byte is changing from a 1 to a 0. And this looks like starting at 40. So we've got 40, 41, 42, 43, 45, 46, 47, 48, 49, and then 4a is where that value is changing. Okay, so we just want to make a note of that address, so OX 4a, and that is where in the block that byte needs to change. Okay, and then we know, obviously in the, or not obviously, let's take a look at it. So what we're going to do is take this block, which I've already copied over out to my host, and we're going to open it in an online hex editor. You can use any hex editor you want, but I found this one's nice and easy to view and use. So let's go over to this and open up the block. Okay, so now we can see this is just a hex dump. We've got our hexadecimal addresses here, the actual content, and then this is rendering, I believe, ASCII text encoding. Okay, so we know at address 4a here, or I guess this is actually 49, so I was off by 1. Okay, so at 49, we know this needs to go from a 1 to a 0. And then also in our PDF, we can see the PDF basically comes after this original block data. So this kind of defines different attributes about the block. And then what happens is we go into the first file and then the second file. So our first file is come back out here and do xxd .bin. So this was the first file that this block has, and so these are the contents of it. So EA46, we'll remember that. Come back into here. Where does EA46 start? Right here. So this is where the binary blob starts that was inputted into this block. And then this looks like where our PDF starts. Okay, so we can see that this right here, this is our the comment that we saw previously. This is the value that we need to change from 2 to 3. So let's go ahead and make these changes. So 32 hex is going to be changed to 33. Okay, and then we also need to change this this nice score to naughty score. So we're going to do, I believe, 30. Yeah. So we've decremented this one and we've incremented this one. All right, so now our two changes are in there. Now, if we were to save this out to a block and think, hey, this is our original, and try to take an MD5 hash of it, we'll notice that it's actually not the same, and there is no collision going on. So we need to figure out a way with these two changed bytes to change 2 more bytes to make this essentially clash with the previously modified block. So we were tipped off that this uses the unicall type hash collision, and this great deck, which is quite long to read through but gives a lot of insight on hash collisions, talks about unicall, and basically the important details here are there are 2 collision blocks, and the differences are the 10th character of the prefix you increment by 1, and then the 10th character of the second block you decrement by 1. And it gives an example here. So here's like the original, and here's the colliding block. You can see that this is the byte that's being modified, and then exactly 64 bytes later, because that is the ND5 block size, we can see that since this one is being incremented, this value is being decremented. Okay. So we need to essentially make that change in both of the bytes that we changed ourselves, so that this thing will hash collide, and then we can get the same MD5 hash out of it. So if we go back to our hex editor, we've got this, and we know that the MD5 block size is 64 bytes. So at address 49, we need to add what the hex decimal equivalent of 64 is to this address, and then we need, since we decremented this, we need to increment the value that we're going to change 64 bytes later. And then for this, same thing, except we incremented this, so we need to decrement the other value that we're changing. So current address is 0x49, so let's go open up our hex calculator. Decimal 64 is hex 40. Okay, so 64 bytes in decimal is 40 bytes in hexadecimal. So we'll click on hex here and do 49 plus 40, and that gives us 89. So we'll come out to here, and this D6 byte, this is at address 89. And again, so because we decremented this value, we need to do the opposite to this. So we need to increment this. So this should actually be turned into D7. Perfect. Let's deselect this so it's not confusing. Okay, so now we have 3 out of the 4 changes necessary. And I guess a caveat here, the reason we're not going up to make changes up here is because if we did, this would actually modify important parts of the block. Whereas if you remember, this starting here and going to basically here, this is the binary blob file that was attached to this block, and that doesn't really do anything to modify the way the block works or what it represents. So we can change anything safely here. So we go down to this value by 64 bytes rather than up to make those changes. And then the next thing here, we have incremented this from a 2 to 3. So in hex, that's 32 to 33. And so now we need to modify in the second block to basically be decremented rather than incremented. Okay, so what we're going to do is take this address of 109 in hex, and we're going to add hex 40 to that, and that gives us 149. So if we come down here, this value is at address 149, and we need to decrement that to 1B. Okay, so now we're at a point where we've essentially made the proper changes to do a unicall MD5 hash collision. So if we save this back out, we'll essentially be reverting the changes that Jack made, getting the original block, and then we need to take the SHA-256 sum of that, and then that is what we will submit as an answer. And to verify this, we can take the MD5 sum of both this block and the original block, and if they match, we know we have our collision. So let's go ahead and save this as modded final.block, and we will copy this back into the Linux box here and paste it in. And then if we do MD5 sum modded underscore final dot block, and then we do MD5 sum the original block here. We can see that they are exactly the same. So we were able to make modifications in the block that drastically change, how it acts and what it represents, but end up with the same MD5 sum. And to anybody verifying the blockchain, they are none the wiser that this massive change has happened, and nobody can detect that with MD5 sums. However, if we do SHA-256 sums on these two blocks, we can see that they are vastly different. And so in this case, This is a lot safer of a hashing algorithm to use because somebody would have detected this change as soon as a test was run against the blockchain. So we can see that this is the SHA-256 sum, and believe it or not, this is actually the answer for what you would submit here to get the solve for the final challenge of the 2020 SANS Holiday Hack event. So this is quite complex. I kind of breezed over some details about the collisions and how exactly my trial and error process of discovering this went. So be sure to check out this slide deck and work through this video on the blockchain, and then also this collisions repository has a lot of good information about colliding certain types of files. So if you have any questions, let me know. And otherwise, thanks a lot for checking out this walkthrough. That is the final challenge. So we'll see you next year.